Alright guys, unfortunately this video is not really going to contain that much progress. In fact, it may be a case of one step forward and two steps back. In fact, it's with a bit of hesitancy I put this out. Things over the last few months didn't really materialize, and as to what that entails, well, you'll see over the course of this video. But hopefully it's entertaining nonetheless, but it wasn't the progress update I was hoping it would be. So as per the last video, this is the power supply that I bought for the sake of driving the laser. Now I'd bought this under the pretense that it had some form of rise time control, and technically it does, but it doesn't when it's being operated remotely. What you can see in the right hand column is a series of time presets, and if it's left to run continuously, it will switch between the voltage and current settings and increment over the interval that has been set. But if it's triggered remotely, it just jumps between the settings. Now the reason I actually wanted this rise time control was to ensure that no overshoot would actually kill the laser. Unfortunately, with these fiber coupled diode lasers, transients are a real risk when it comes to the longevity of the device. It only takes a couple volts in reverse bias to actually end up killing the unit, and when you combine 16 amps with long leads or the inductance of the long leads, there's a real risk that overshoot could potentially kill the unit. So what you're looking at here is a little test rig that I put together just to see how bad these transients were going to be. Now the laser I've got here was the first fiber coupled diode laser that I had bought for the sake of this metal 3D printing project. Unfortunately it's not good enough and I ended up damaging it anyway, so I'm pretty happy to actually destroy it just to ensure that I'm not going to do the same thing to the new laser that I've bought. Now the laser itself is called a FAP 800, which stands for Fiber Array Package 800 micrometers. It's a bit of an unfortunate naming convention, but you can find these things pretty cheaply on eBay for around 100–150 USD. There's a few other variants available as well. There's 600s, 400s, even 200s, but the 800 seems to be the most common. Now these units can be a little bit awkward to work with. They typically have an operating voltage of anywhere between 1.8 volts to 3.3 or 3.4 volts, and they typically draw between 40 to 60 amps of current. This unit here is rated at 50 amps, but I'm not going to be pushing that hard today. The maximum output of the power supply is 21 amps, so I'm going to push it up to that and see how well the power supply performs under load. Okay, so the way I've got this set up is that the red trace represents the voltage across the terminals of the laser diode, the yellow trace represents how much current is going through it. Now the first thing I'm going to look at is the positive going transition. We're just going to see if there's any overshoot there, and what you can tell from this is that the power supply is set to constant voltage mode. Now because of that, you can see on the current curve there's a little notch there, which is basically the compensation circuitry kicking in, stopping the voltage from rising any further. You can see it's heavily damped, and because of that it's sustaining the voltage. Now this actually surprised me quite a bit. I didn't expect it to perform this well, mainly because the voltage is referenced from within the power supply and not at the terminals of the laser diode. I expected the inductance within the lines to cause a little bit of overshoot, but it seems to be fine. So the next thing to look at is the negative going transition. I think we can infer from the positive going transition it's probably not going to be a problem, but it's worth considering anyway. This is where overshoot is going to be more detrimental, as this device is not intended to handle any reverse current. So this time I ramped the device up to over 20 amps and then suddenly switched the unit off. As you can see, there's no problems with overshoot, the current doesn't cross the zero crossing line, and the voltage just kind of bleeds away. Now I ran this test a couple more times to see if I could catch it out. Unsurprisingly, wasn't an issue, but you can see that there's quite a bit of noise, particularly when the unit is switched off. And I don't actually think this is from the power supply. I think this has more to do with the current clamp that I'm using. Because there's quite a bit of background noise where I'm working, I think this is coupling into the current clamp. Now I should probably mention that this is by no means a paid review. If it were, it would probably be a pretty poor one, but I'm just testing this in the context of the application that I'm going to be using it in. Now I have to say, based on that compensation circuitry, it's probably not going to be able to be switched on and off very quickly. Not that I'd want to do that anyway, but it's just something to be mindful of, particularly if you're intending on using something like this with galvanometers or something like that. Okay, so now that I was a little more confident that the laser wasn't going to be destroyed by the power supply, I set about making the heatsink for this unit. Now I want to make a brief reference to the Backyard Scientist and a video that he put out in which he mounts a 200 watt laser to the top of his car. Now the laser he uses in this is almost identical to the unit I'm using. Now he copped a bit of criticism for doing this, but in his defense he had said that he had checked the flight paths, that the laser intensity wasn't that great, and one of the more interesting points that he made was that he wasn't able to run the unit at full power. In fact, he was only operating it at 50 watts in the video. And the reason he stated for this was that the maximum operating temperature of the laser was being reached. Now if we look at his design, it looks like he's made himself an aluminium heatsink, and if you go and watch his video you'll see that he's operating within a relatively confined space. The water ballast doesn't look that big and the pump is quite small. Now even though his cooling system suffered from some limitations, I still wanted to base mine upon it. Unlike his system, I'd have a lot more water at my disposal to keep the system cool. On top of that, I would source copper heatsinks instead of aluminium. I would cool both the underside and top of the laser unit as well. Now, even though this isn't the best way of doing things, I still wanted to give it a chance because if I had to buy a cooling system, it was probably going to be another 800 to 1000 USD. To make matters worse, these systems can't tolerate any condensate on them, so it would have to operate within some sort of sealed environment. And really, those are complications I'd like to avoid. Now, something else I probably should have mentioned before is the low temperature thresholds for these devices. This one's not too bad at 55 degrees Celsius, but if we consider the FAT that has a maximum operating temperature of 40 degrees Celsius, some of them even have temperature thresholds as low as 30 degrees Celsius. Hence all this concern over keeping the unit cool. Now, in all honesty, this is part of the reason why I've avoided using one of these laser modules up until now. They're quite delicate, you have to take care when operating them, but this is the price that has to be paid if we want to attain a higher power density. So with that out of the way, it was time to set up the lens assembly. Now, as per the last video, I said that I wanted to stick with a single lens element. So the first thing I wanted to do was test out whether that was going to be possible. Now, unfortunately, because the laser operates in the near infrared band, this means it's no longer easy to visually inspect whether the lens is in focus. So to make life a bit easier, I happened to have a broken fiber on hand, and I would simply inject light into it so I could see whether the lens is actually in focus. Now, I'm just using the LED off an old cell phone and injecting that light into the fiber. Since the fiber is 800 micrometers, and given that we have a back focal length of 26mm and a forward focal length of 40mm, I was expecting the focused spot to be about 1.3 millimeters. And when the fiber was weakly coupled with the light, this happened to be the case. But unfortunately, when the fiber was strongly coupled with the LED, you can see that a lot of light wasn't able to be focused into the focal spot. Now, I suspect the reason for this is that with the fiber 2 focal lengths away from the aspheric lens, that the effective aperture of the lens isn't large enough to focus all of the light. And because an aspheric lens uses a relatively aggressive curvature, a lot of that light is just being focused around the focal spot. In the past, I've used a biconvex lens to do this and it's worked fine, but unfortunately in this scenario it isn't going to work. So therefore I would have to resort to using a multi-element system. Now, because I didn't have a lens with the correct focal length on hand, I ended up combining a 100mm and 150mm lens to form a 60mm focal length. And since the back focal length of the collimator was 26mm and the forward focal length of the two lenses was 60mm, this would mean that the focal spot would be over double the size of the fiber. And when used in conjunction with the new laser, this would translate to a spot size of about 460 micrometers. So with a spot size of 460 micrometers and a power output of about 200 watts, theoretically we could achieve a power density of around 1200 watts per centimeter squared. Now, this is actually pretty low. In fact, we'll be stuck in conduction mode if that's the case, and this doesn't even account for the losses due to the window of the enclosure. I set up a small test to find out how much power would be lost due to that window, and what I found was that it was around 14%. So it's gone up by about 6% due to the increase in wavelength. So if we account for 14% due to the window of the enclosure, plus another 6% for the 3 lenses, we've lost about 20% of the power before we've even hit the substrate. This would lower the power density down to about 960 watts per centimeter squared, which was even lower still. Now, before we dig into this any further, I want to make reference to a commercial 3D printing system that started off with fairly humble beginnings back in 2014. Now, this is the Kickstarter page where they launched the project initially, and they were offering these printers at $4,500 to $8,000 Australian. Now, their system is CO2 based, and from what I can tell, it was made with some fairly generic parts. And a few years later, a paper was released basically performing a teardown on this, analysing the operation of the machine and the results it produced. You might notice from this campaign that the funding was cancelled. I don't know quite what the reason behind that was, but I have a feeling at the price point that they were offering it for, turning a profit on something like this would be near on impossible. Now, I want to make reference to this printer specifically because I need to give some context to the numbers I'm throwing around, and since this printer uses a non-ideal laser source for metals, I think it might provide a good benchmark as it sets the bar fairly low. Now, this printer is equipped with 250 watt CO2 lasers, and with the system configured to full power, these would produce 240 watts. Now, the amount of power measured at the bed was 160 watts, meaning that there was a 35% loss across the mirror assembly. This system is Cartesian based, there's no galvanometer or anything like that, and they happen to use a 100mm focal length. Now, as to why they use such a long focal length, I'm not too sure. I couldn't quite tell from some of the pictures whether this actually has a soot extraction system, and if I were to guess, maybe they were using a longer focal length to avoid any soot from actually contaminating the lens. Now, because of the larger wavelength and the longer focal length, this was only able to achieve a spot size of 0.5mm and in turn produced a power density of 800 watts per millimeter squared. Now, a CO2 laser is obviously very different from the laser that I'm using. So for example, a CO2 laser might have a m² factor close to 1, meaning that the beam is close to Gaussian, whereas the laser I'm using is pretty far from it. Now, to contrast this, CO2 lasers tend to have very poor absorption characteristics, and it wouldn't surprise me if some of the losses that were being incurred were due to damages occurring across the mirror assembly due to reflection. Now, I specifically wanted to make reference to this paper because it shows how significant some parameters can be when other inputs are not ideal. For example, the part density doesn't really exceed 95% until the hatch spacing is brought down to 0.3mm, the layer thickness is down to 30 microns, and the speed is reduced to about 25 to 30mm a second. But all in all, this is done with a power density that would firmly see the machine operating in conduction mode. Now to contrast this, many commercial machines take advantage of something called keyholing. This is where the power density is increased to such an extent that the metal boils, forming a stream of vapor with enough recoil pressure to open up a well beneath the stream. This well acts as a light trap and significantly increases the energy absorption, resulting in greater efficiency. Now this brings with it many advantages: speed, greater welding penetration, less residual heat, to name a few. But as this process leans towards instability, without a firm model to build upon, this has the potential to create many issues as well. This is a fairly in-depth topic which I will delve into at a later stage once I have the power density to support it. But initially, I'll be seeking to replicate something similar to that previously mentioned. So after setting up the lens assembly, I proceeded to level the bed. Now this is a very painstaking task given the amount of time it takes, and really points towards some deficiencies with this current setup. Since the powder bed is effectively floating on 2 lead screws, there is a lot of potential for error. To make matters worse, even though the laser head is mounted to a linear rail, since we want accuracy in the order of micrometers, there is still an unacceptable amount of play. You can see the lack of repeatability in each of the measurements I make, and any inconsistencies in the machine deck would only further contribute to misalignment. Because this laser source is highly divergent and requires a larger focal length to effectively collimate, and conversely when focused, the beam also has a sharper convergence, this means the depth of focus is much shorter, and any misalignment will have a greater impact on the ability to achieve peak power density. Now there are a few ways to combat this. Obviously, the first step is to get rid of the core XY frame. I think this is a given, but leaves the question of how to manipulate the beam. I had been hoping to use a Risley prism scanning method for the sake of beam steering, as this has a larger aperture and would easily couple with the existing hardware, and the role of the f-theta lens could simply be solved by shifting the focal lens in accordance with the rotation angle. The problem with this approach is that by the time you have bought 3 high quality prisms, you have spent close to 200 USD. And this still leaves you with minimal deflection. Furthermore, the reflection and distortion brought about by the offset faces of the prisms is particularly unattractive. Now I know everybody loves the effect of galvanometers, but at this point in time I don't think they are the right option. Because collimating this beam relies on a large degree of expansion, and most generic galvanometers have an aperture size of 10mm, unfortunately they aren't suitable. Now you can get galvanometers with an aperture size of 20mm, but by the time you have sorted one of these and a suitable f-theta lens, you're looking at 700 to 800 USD. Even then, because the power density is too low to support rapid scanning, this will be constrained to Cartesian speeds. So I'm most likely going to stick with a Cartesian system for now, and mount it to the top of the gas enclosure. Getting back to the topic of alignment, there are still issues with the Z-axis. Now this has come a long way since some of my earlier attempts, but still needs further improvement. Referencing the paper I mentioned earlier, you can see how much difference 10 to 20 micrometers can make. There are obviously other contributing factors in their test results, but these other factors are easy to control for. Here I'm stepping in 30 micrometer steps, and you can see the movements tend to wander back and forth. This is due to a bit of bad design on my part, as I used the weld seam of the bores to locate the pistons. These have slight variances in them, and since the lead of the ball screw is 4mm, each tenth of a degree translates to a micrometer of movement. Furthermore, the use of 3D printed parts is too much of a compromise, and I've also been told that cheaper ball screws can suffer from tolerances bad enough to cause these problems. From the beginning I've wanted to keep this as cost effective and DIY friendly as possible, but it seems that this is going to need an all metal assembly. Something else I don't think I've touched on to date is gas consumption. Typically this takes around 80 to 100 litres to purge down to 0.2%, and I'll typically start purging at 5 to 6 litres per minute and then reduce the flow to 2 litres per minute once the O2 levels get down to about 0.5%. Usually this takes around 15 to 20 minutes, and I'll sustain the run at 1 to 2 litres per minute. Now with everything I've mentioned, I still wanted to see how the new laser was going to perform. To begin with, I set the power to 100 watts and performed a few test runs. The first was to find out the correct height for the laser focus, and the second and third were just testing out different lens setups. Even though the single lens element didn't concentrate all of the light into the focal spot, I still wanted to see whether there would be enough energy to form a continuous track and how it would compare to my predictions. You can see the tracks are fairly discontinuous and there is a lot of shadowing. Where there is a continuous speed, the average track width is around 0.3mm, narrowing as the translation speed increased. This third run was performed with the multi-lens array with a focal length of 60mm. You can see the tracks are much more continuous, but notably have a lot of balling occurring near the edges. These runs were all performed at 10mm a second, as I wanted to see how level the substrate actually was relative to the laser, as I'd been using a different method to level the substrate. The bottom track is notably more consistent than the tracks above it, so there is some evidence of misalignment, but this could also be attributed to the leveling of the bed. I suspect the balling probably has a lot to do with the slow scan speed, which is due to having a power density of around 430 watts per millimeter squared. And this is confirmed by how these tracks don't effectively wet the substrate. Because of this, multi-layered runs are impossible as the tracks sit above their intended layer height, resulting in the spreading blade making contact with them. So the answer to this is obviously to raise the power, but before I got the chance to do this, disaster struck. I'd been making changes to the lens assembly, and I suspect when doing so I had got some dust on the end of the fibre. Now, unfortunately I wasn't filming when this occurred, which is a lesson in itself, but I can say that when this happens, it's a startling experience. So I had two options at this point: send the laser back to the manufacturer and wait 4 to 6 weeks for it to return, or order the tools to cleave and polish the fibre and do it myself. Now obviously I went with the latter because of how quickly the situation arose, but even still, it would be a matter of weeks before I got the tools I needed. So in a bid to get something worthy of interest together, I returned to an earlier configuration. Since I was returning to using an NUBM series laser, I wanted to explore something I had never got around to. Because of their shorter wavelength, generally these lasers have better absorption characteristics for most metals, and this extends to pure copper, an otherwise highly reflective and difficult material to work with. I had some copper powder left over that I had bought a long time ago. Unfortunately, this powder was produced using water atomization instead of gas atomization, meaning that the individual grains aren't spherical. This relates to the packing density of the powder and contributes to the overall part density, but as the power input is low and given the limited nature of what I'm doing here, I don't think we have to worry about that. On a side note, metal powders made using a water atomization process tend to be a lot cheaper, but lack the same standard of grading. But depending on what you are intent on making, these may be a suitable substitute. I've come across a couple of papers that suggest that water atomized powders can yield characteristics on par with gas atomized powders, but since starting this project I have found that you can source gas atomized powders from abroad for fairly cheap. However, the cost of shipping is still prohibitive. Since I was doing this on a whim, I decided to use the NUBM31 I had lying around, just to keep things simple. This would be shy of around 35 watts compared to the laser head using the two NUBM38s, so to compensate, I mounted the window further down into the enclosure so I could use a shorter focal length and achieve a tighter focal spot. I made a new cradle for the laser, this time cooling the unit with a copper block, and I set up a run limited to a single layer, tilting the substrate to see how each track would build. Again, travelling at 10mm a second. And this was the result. Ignoring the misshapen track at the bottom, the 3 tracks above it were printed on a semi-transparent layer of copper. I'd estimate around 10 micrometers thick at 10mm a second. As for the top track, this was printed at 10mm a second as well, but on a denser layer of powder, perhaps 50 micrometers in height. Now as for this track, the height of the powder was somewhere in between and printed at 20mm a second. You can see from the topmost track that at a layer height somewhat representative of what is typically used, there isn't enough power to form a nice profile, suggesting that this wasn't going to work as I had hoped. I will say that I am surprised at how easily these formed coherent tracks when compared to stainless steel, and how well it bonded to the substrate. But as the Z-axis wouldn't provide the accuracy I needed, I decided to leave this just as another set of tracks. Now dealing with this powder turned out to be quite a different beast. Despite copper being more dense than stainless steel, clearly there were finer particles present. And because of this, some of the powder remained airborne well after I'd finished working with the printer. I ended up being exposed to it, which left me pretty unenthusiastic about pursuing things any further. In fact, given the way things had gone with the laser, the need to once again revisit things I had already addressed, and the lack of overall progress, I was feeling pretty disillusioned with the whole project. I'd been wanting to work on some other ideas, so I disassembled the printer and shelved the powder bed. But after the honeymoon period of working on a new project had passed, I realised that it was probably past the point of no return, and that it would only be a matter of time before a new set of issues got the better of me. So I have a couple of videos planned where we will work on ways to fabricate metal parts necessary for that printer, as well as some other work around wire-based metal 3D printing. Until next time, guys.